Next presenter and second keynote speaker is Nicolai Josuttis. I'm pretty sure that some of you have gone through some of his many C++ books over the years. So, well, I was telling yesterday when I joined the committee a long time ago, he had already been there for a long time. So are you older than me?
I think so, yes.
So he is a member of the ISO C++ committee for a long time. He is a well-known C++ trainer, and I would say he's also a specialist in finding holes in the standard. I don't know if this was a compliment or not, but you are quite good at that.
Good.
Okay, so and he is going to talk about filters and views. So if you are not familiar with ranges, you should.
Or maybe you shouldn't. We will find out. So, okay. Thank you very much, Daniel, for the introduction. Thank you for the invitation. Let's talk about something brand new. Well, is it brand new? Well, it was introduced with C++20. We were introducing views. And I would like to talk a little bit about that. Now, just one view, the one view we have, which is a filter view, you will have fun, for sure. So, we talk about something that was introduced in C++20. We already have a couple of fixes in C++23, and new things are coming in C++26. But what I just talked about is already 3 years old or 4 years old. And we have some experience now, and that creates interesting use cases and interesting opinions on this topic. So just for those who don't know about details, what is a view? Well, if you have, for example, a vector and you have a print function, you can have some function template that takes an arbitrary collection of elements and call this function print, function template print, iterate over the elements to print them out. And that is generic code. This works for sets, but this also works for other things. But before we look at that, let me just say in C++20, it's enough to declare the parameter as auto instead of introducing a template parameter for that. And if you like, you can constrain this type to say, well, give me a useful error message if this is not an input range, that is a range where we can iterate over from begin to end. So that can be used now in by different things. And one of the things are views. Views are a feature that is not a container. We don't create something new having elements. It's just that we have a recipe to deal with the elements of an existing container, or in more general, of an existing range. So here you see one view, which is just taking the first 3 elements of the first collection, and the same is possible for the second collection. And you see that the interface of this view provides the usual API to iterate over elements, so begin and end, and using an iterator to print them out, because that is what the print function template on top uses. There's an interesting other syntax to use it. It's just a different syntax. That is, you can use a pipe symbol, which looks like we pipe the elements of the collection into a take view, which is not exactly right. It doesn't work like in Unix. But roughly, essentially, it looks like having the same effect. That is, we can just take any range and pipe it into some way of processing both the elements we use and their values. And of course, you can have complete pipelines like this one, saying, let's take the first 3 elements of the second collection and do a transformation with the values, converting them into a string and appending an S, and all this is passed to print, and there's a result. Awesome technology. No filter yet. So let's talk about filters, which are one of these views. So looking at a few other examples. For example, here's a map. Map is a container where the elements have keys and values. So the key is here, composer of classic music, it's the name. And then the year of birth is a value we map. And then you see, let's use this map and iterate over the composers, but not only over the composers. Let me, instead of these composers, use only those who were born since 700, and then takes the first 3 of them, and then take only the keys, which are the names of these key value pairs. And then that's the elements we iterate over, and you see that we print out just these 3 values. If you're confused by Beethoven first, remember a map sorts the elements. Here we, for the first time, see a filter. And you see that a filter can take a predicate which says, I accept elements which have a specific value, where the predicate here, the member second has to be greater than 17, is true. Here's another example. IOTA creates an unlimited range of values starting with the initial value here. So this is IOTA starting with 1. And then let's use a filter, only filtering and accepting elements which are multiples of 3. And then dropping the first 3 of them, taking the next 8 of them, and again converting them to strings and append an S. As you see, you can create and initialize a view with that. The type is very interesting. You definitely don't want to write it because it's kind of a transformation on a take, on a drop, on a filter on an IOTA view. And so auto is our friend here. And then let's iterate over this view. And here's the output. Great technology, awesome technology. Looks very promising that we can, just by combining building blocks, create and describe what we want to do with the elements of collections, ranges, and so on. So to understand this talk, let's look a little bit how this works. So how did we do that in C++? Well, the basic idea is that we use a common API for ranges to iterate over elements starting from begin, iterating until end, and then call ++, and then to go to the next element and the start to see the value. So if we have a print function, it more or less directly or indirectly will call begin, compare against end with an iterator, iterating over all the elements, and as I said, star to go to the value. So if we use that for a vector, like here, yeah, begin gives us the position of 47, then with star we get the value, then with ++ we go to the position of the 11, then with star we get the value, and so on, as long as we have not reached the end. That is the key API for the success of C++. That was the key API to say, we can deal with different data structures and use generic algorithms for them, but also we can program ourselves generic functions with them, and was a big reason for the success story of C++. So we now use that for views. So if we now say, for example, let's filter all the elements in this container which are less than 20 and then negate the values, let's see how this works. It is what we pass here to print is just a shortcut to say, Let's create a filter view initialized with the range we're iterating over and the predicate. This is V1. And you see that V1 is not processing elements yet. It is just a description. It is just a wrapper on the underlying range. Providing the same API, begin and end, plus plus, star, and equals, equality comparisons. And the transformation is then put on top. We now take V1, the filter, and transform the elements to negate them. And that's again a wrapper around the filter view. And here we again provide an API, begin, end, plus plus, star, and equality operations. And that all means that if we pass a whole thing, that is essentially V2, to the print function, a generic print function, that function will again, as usual, start with begin. Begin will go to the transformation first. The transformation says, oh, I'm wrapping the filter, so goes calls begin at the filter. The filter says, I'm wrapping the collection, so goes to the vector and calls begin there. And that means we get the position of 47. But that position is returned to the filter. And the filter says, oh, wait a minute, that's not a value I would like to accept. Well, to do that, by the way, the filter has to call star already. It has to look at the value of this element. So it calls star to look at the 47, rejects it, and rejecting is done in a way that the filter says, that's not something I can give as begin. So it calls plus plus to go to the next element. Internally, the begin call of the filter calls plus plus. And that plus plus will then come up with the position of the 11. The filter asks for the value, looks at the value, says it's less than 20. So the filter propagates the position of the 11, not the value. We talk about iterator interfaces. And that position is passed to the transformation. The transformation is passing this to the caller, because from the calling side, we not yet need the value. We need the value when we then take the value of that position. So that goes from the transform view to the filter view to the container again. Maybe the filter has cached this value, and we get back the 11. But in this case, the transformation says, wait a minute, I have an 11. I should negate each and every value when we need it. So we return with the star operator here, or the transformation returns minus 11, and that's what we print out. And when we call plus plus, the same thing happens by looking at the next element. Plus plus is going through the chain of views up to the underlying range. We look whether it's acceptable or not in the filter, and if somebody needs a value, the transform view will negate the value. So that's the way this works. And of course, it only works as long as we haven't reached the end. So all the time here, we compare begin, we compare plus plus with the end, whenever we call it on all the different layers. That's it. That's the way we implement it. So you see that in contrast to Unix, where when we call a filter, we create temporary containers with elements to then compute and start the next computation. And we need multiple processes for that. Here, we only need one thread. This is single-threaded. And it's just that we have what we call a pull model. That means the next element and its value are processed on demand, going along all this chain. That's a key approach of this design, of filter design. So let's look a little bit at the performance of the whole thing, because performance matters in C++, as you might have heard. So let's use same thing again, collection, filter, and transformation, but let's have print statements here. So as long as I don't use any of these views asks for a position or a value, nothing happens. Just when we call the range-based for loop, that is the moment where we start to process data. And you can see now in the print statement that exactly that happens what I just told you. The filter asks for the value of the first element when we call begin, gets the 8, rejects it, then gets the 15, accepts it, so transform gets the value. When the user of this range-based for loop asks for the value, we iterate with the int value about that. So internally the range-based for loop does not only call begin, it also calls star. And that means the transformation will negate the value, and that goes on with ++, looking at the values until we have the output that you see here, and until we have reached the end. So just for fun, change the order and start with a transformation and then do a filter. And then we have an interesting different output, which looks like this. So far, nothing happened until we start with the range-based for loop. And that means now you see, well, the filter, because the filter has to filter specific elements, looking at the values, the filter first needs the transformation. So the transformation is done first, so that the filter can look at that and looks at the -8. And then, is this a multiple of 3? No. So we reject. We are still in the begin of the filter. The begin then goes, calls the position of the 15. The filter asks for the value. The transformation creates a value, which is -15 then. And then the transformation says, okay, that's accepted, passes this to the outside loop. And the outside loop, again, needs a value. And that is interesting. We didn't cache the value. We had to find it once for the filter. And we needed it later on for the user, because the whole chain works with iterators. We sometimes cache the value if we directly afterwards need it, but not in this case, in cases like this. So you see that we have here multiple calls of transform to at least for the elements that are accepted by the filter. And yeah, the rest is the expected output. First lesson learned here, use a filter early. Because if you have a filter late, it might be that processing that is happening, especially on the values, has to be done multiple times. And with each and every filter, that adds on. Good. So this looks like a nightmare. Also having a lot of different types, a lot of different functions. How bad is that? Well, remember that all this design is single, simple functions, inline functions. And compilers optimize a lot. So they can optimize away more or less each and every call here. So essentially, what we compile here is something like this. We say, let's start with a range, iterating over a range where we call a filter and a transformation, which is essentially, let's iterate from begin to end over the core range, the basic range, and then use a filter and a transformation to decide what to do. And that means we multiple times call star pos to look at the value, once that the filter can decide, and once because the user then needs the value. But process, because the transformation is done after the filtering, then also calls negation on that value. If we have it the other way around, so transform pipes into the filter, we have, you see that the filter already needs a transformed value. So that means, as you see, that we negate the value twice. So one in the if clause and one when we process the data. And that is more or less essentially the code we write. So is this fast or not? Is this a problem or not? Well, if minus is cheap, then it's not a problem. And then compilers can optimize, at least sometimes. If the transformation is pretty expensive, it gets more interesting. Then definitely the second code might become a problem. So that's a model you program now by combining these building blocks, and you have to need the best support by the optimizing compilers. We are at the beginning. Don't be very scared if the performance is not perfect yet, unless you have to deliver software today, because we are still working on optimizations in this specific area. Standard compilers learn over time which are typical use cases and improve their with priority. Is this the only thing that worries us about performance? Well, let's look at the individual operations called here. So one interesting operation I would like to look at is begin. So assume I have a filter on a vector, accepting all the values that are greater than 9. Here on the vector, that is internally having all the values stored in some heap in some heap memory. So when we call begin, then the following has to happen. Begin means that at the end of the call, asking filter which one is the begin, the first element, which means the filter has to find the first element that fits. And that means we call begin, but we look at each and every value to find out which one is the first element greater than 9. This calls begin once, plus a couple of times, and a couple of times, because we always have to compare against end to see that to make sure we are not beyond the end of the container. And at the end, we find 47 is the position of the first element that fits, and that is then returned by the filter. This means begin is not cheap. Depending on the probability of where the first element that fits the filter predicate is, this can become a problem. So if you have 1 million elements and the filter is used only to find one of these 1 million elements, in average, you need 500,000 increments on 500,000 calls of AND. If you have a different use case, and the use case is you have, I don't know, values 1, 2, 3, 4, and with equal probability, so more or less at the beginning, there will sooner or later be an element that's, no, I need something with greater than 9. So in that case, if we only have 1, 2, 3, 4s in this filter, and we'll iterate until the end of the view of the collection. There's no element. So that's the worst case. If we have values between 1 and 10, or 1 and 20, and some of them are greater than 9, so it's pretty likely that one of the first elements is greater than 9, then it's okay to have this. And the same is true if we use other containers underneath. So if we say, okay, let's have a filter on a list, same thing. Begin, calls begin, we have to iterate over the elements, look at the values to see which one is the value that is the first value that is greater than 9. So begin is not cheap. Well, begin is expensive on filter, on vector, and is expensive for a filter on a list. Well, we can say it has linear complexity. That is, the more elements we have, the more it might cost. Well, which is not exactly right, because if I have a use case where the probability that the first elements have an element greater than 9 is independent from the size, then this is not a problem. This is not linear complexity, but that really depends now on the use case we have. we don't like bad performance in C++. So we really try to avoid supporting bad performance. So that's why a vector does not have push front, because inserting an element at the beginning has to move all the others. That's an expensive operation. That's why a list does not have the index operator, because if I call the index operator to jump to the 100th element, I have to iterate over the first 100 elements to find where it is. So therefore, we disable expensive calls. And we did that in the past. So the same approach is at least something we thought about here. So let's look here in this collection, in this scenario, and let's see which one are multiples of 4. Well, obviously, the fourth element is the first multiple of 4. So begin would have to find the 4. Is begin expensive or not? Well, I would say it's slow because it might depend on the size of the container, and it grows in the worst cases linearly. There's some music around here. Good. The fun parts to have a fanfare come later. So, how about AND? What do you think? Is AND good or bad? Is it slow or is it fast? What do you think? Who thinks this is a fast operation? Who thinks this is a slow operation for the same reason as begin? Because we would like to cache the end. We would like to find the end. It's fast because that's very easy and just returns the underlying end. That's it. That's at least how we designed it. So please note, we don't return the position of the 13. So we don't look at the values when we call AND. How expensive is empty? Similar to begin, because more or less you can say we call begin and see whether begin is the end. But that's not exactly true, because empty needs to iterate over all elements, because end is not using the 13 here. Size. We have to look at each and every value to see whether it matters. It's expensive. Front. Give me the value of the first element. That's easy. Like begin, go to the element and go to the value. And back. Similar. If we can come from the end at least. So we can say, let's go to the end and iterate backwards. If that is not possible, it gets more interesting. So we might have to iterate over the whole thing and then cache somehow back the last element. Index operator, also expensive. It's because we have to find the third element that matches if the index is 2. Slow. As I told you, we don't like expensive calls, so what we do is we disable that. Well, we don't disable begin. That would be a little bit of a problem because we can no longer iterate over the view. But we can disable size and the index operator, and to some arguments, front and the empty is more or less, if we have begin support, it's more or less the same. Well, that's at least the API we have in this scenario, having a filter on a collection like a vector. But how can we improve the situation? Well, the designers of the filter view thought about it and came up with a great solution. The great solution is when we have a vector and we have a filter on the vector, and we call begin, which means we have to look at the first element until we have a match, that element is cached. So we start in the filter view. And we do that also, of course, when we iterate over the elements of a list. Please note, we don't cache end. End is the end. So it's not the position behind the last matching element. End is the position, the last element. The way we design the filter view. We have a couple of views that cache. That's in C++20, where we introduce a couple of like 15 or 20 views. Some of them cache always, and some of them cache sometimes, which I don't talk here about, but which creates interesting effects. Now, we might have get into a problem. And the problem is somebody has called begin for the vector and then inserts a new element. That's not good. Well, in a list, it's fine. In a list, because inserting new elements somewhere else does not invalidate iterators. But when we have a vector and we have an iterator there, and we insert new elements so that we have to allocate new memory, the iterator to the 47 becomes invalid. So here, for example, we might allocate new memory somewhere totally different. And that is a situation. But we are smart. So what do we do here? We don't cache the iterator, we cache the offset. And the good thing is, it's cheap to jump with an offset to an element in a vector. So remember, and that will become interesting later on. Filters cache always, sometimes an iterator, sometimes an offset, depending on what you have below. Okay, with that, I could say, well, looking at how expensive are the operations, some of them are slow only once, not multiple times. The standard specifies that behavior. First of all, it requires caching. And the standard says, you know what? If we have the behavior like begin, first time is expensive, but next time it's cheap, then we have a term for that. And that is we are amortized constant. That is, once we are expensive, but later on it might be cheap. We have that when we push back elements in a vector, where we say, well, once you might have to allocate new memory, have to copy all the existing elements, but then next time, because we allocate not only one memory for one more element, we maybe double the amount of memory, so that the next pushbacks are all cheap. And over time, this amortizes. So that's also what we hear. And then in fact, we have a description saying what is the essential semantic and requirement of a range. And it says not begin and end is cheap. It says begin and end have amortized constant time. Good. That's the design. The design looks great. Let's see, we have half of the talk over. So now let's only talk a little bit about the consequences of this design. One of the first consequences you face is the following scenario. Yes, you are starting to use views. You like it. So you say, oh, let's have a generic print function. Let's take a vector, let's print the elements of this vector, but let's also play games with views. So let's take the first three elements. Great. Let's transform the elements and negate them. Great. And yeah, let's use a filter and only use the ones that are greater than 9. Great. Works. Oh, no, does not work. This does not compile. You get a crazy error message. Now, if you're at this moment, believe me, I was in that mood, which I just tell you. I was totally confused. I said, what the hell did I do wrong? I didn't know about all the details of design of filters. You know already, so you might have some guesses what goes wrong here. Maybe you have, maybe you're not. But the next thing you try is, maybe the problem is in the print function. So you directly iterate over the elements, putting a vector piped into a filter on the right-hand side of a range-based for loop. That compiles and works. Awesome. So what the hell is wrong with print? Who has an idea what the problem is? It is const. And why is that a problem? Because we cache begin when it's called. So which means you cannot iterate over a filter view when it's const. That's the first consequence of this design. Okay, we're at the beginning of the interesting part of this talk. So, when I teach, there are questions. So, okay, here?
Why isn't begin mutable?
Why isn't begin mutable? This question comes all the time. Give me 3 slides and I will explain why. And you had the same? Well, you on standard committee, you should know that.
I can point you to an arbitrary place in the Senate. I guess the chances are high that you wouldn't know what it's about.
Yeah. Nobody in the standard committee understands the standard as a whole. That's not a problem. It's just a feature. It is just we have 1,900 pages and nobody can understand them all. There's no way to do that. So, mutable we will look at in a moment. I promise. So let me first talk about the question is how can we deal with that? And so what should I teach now to programmers? What should they do? The question is what could they do? So one interesting thing is you can do this. You can say, oh, let's take the vector piped into a filter and then initialize a subrange with that. A subrange is not a container, it's a view. Just the naming convention is screwed up. And the view internally stores begin and end. So we initially in this view call begin and end. So that means we call begin and end. And then we start to iterate. Well, we no longer have to cache. Well, to some extent we have cached in the constructor. And then we no longer have to modify the state of the view when we iterate. So this works. So this might lead to the obvious question, why doesn't the filter view cache begin in construction time? Because then the declaration would already run over all the elements, potentially. So the construction would be expensive, not the first call of begin, which we considered to be worse. Maybe it's not. It's a design decision. It's a trade-off, and we had to make some decision. Okay, so that subrange stores, caches begin on initialization, and that's a trick. By the way, unfortunately, due to language rules, you cannot have that in one line. So you cannot pass fv directly, the thing it is initialized with, there to the constructor, that has to do with some problems of class template argument deduction, for those who want to know that why. Good. So do we have other options? Yes, we can pass whatever we pass to print by reference, but not without making it const. Well, it does not work that you remove the const here, because then temporary objects are not allowed. You have to use what we call universal or forwarding references. That's auto with 2 ampersand. We might have seen that when you looked at details of move semantics. Well, what that means is we can refer to everything, L values and R values. That's why this is called universal references. And initially it was used for perfect forwarding in move semantics, which is a little bit of a confusing term, but the standard committee used that term even after the standard, the community introduced the term universal reference already, which is confusing because this is not forwarding, this only has the potential to support forwarding val. So the correct name would be potentially forwarding reference. But that would be too long. Well, move does also not move. So in move semantics, every term is a fake. Donald Trump would say. Okay, so I call it still universal reference because that's a better term for that. But universal reference and forwarding reference is the same. It's a reference that can refer to temporary objects and to objects that have a name without making them const. And that is what we need here. And yes, this works now. So I only have to explain now in my beginner training, because views are so great, I want to teach that now from the beginning, what universal references are. Peter?
I'd like to object, teach beginners pass by value and pay the price for copying a vector.
So Peter says, teach beginners class by value and then pay the price. Can you remind that, please? So you think pass by value is as good as pass by reference?
It's better.
It's better. We will come to that point. We still have 15 minutes left. Good. If you do that, be careful. So if you don't make that const, you should not concurrently use the view. If you start a thread that iterates over the elements to print them out, and then in your thread, you accumulate the values, what do you do here? You call concurrently begin in 2 different threads. This begin is no longer thread safe. In the standard, we have so far specified all containers, all begins on all containers are thread safe. This is no longer true. Well, it's still true for containers, but not for views. So concurrent iterations are a problem. And please note, calling begin also means calling empty. So one thread calling empty, the other iterating over the elements is a problem. There was a nice suggestion. Oh, and by the way, that is if you use mutable, you hide that problem. So we would say, okay, well, if we make that mutable, we would have to make the begin position. We would have to make it atomic. That's what we should do. But that was too expensive. So in this case, you please use const autoreference. Oh, there's another interesting statement. Before you do that, call empty. Just call empty. Well, because empty initializes the cache. Well, we have in the standard introduced that all containers calling empty, not using the result, get a warning, is no discard, and no, you should disable this warning here. Interesting consequence. Okay, but now I come to Peter, and let's pass by value, which in this function makes the passing the vector expensive. Okay, beginners can program expensively. Sooner or later, I have to explain something here. You can say, wait a minute, but in this case, let's require that we only pass by value, requiring that we have a view. We have a concept saying it has to be a view, so this will no longer accept the vector, and that means we get an error here now. And then you can say, but take the elements of a vector and convert them into a view. That's the all view that will do the task for you. Well, this is not the all view. We don't have an all view. We have an all helper function that creates a view inside that does the job. Or some fun, let's implement print twice, once by value, once by reference, and the reference one calls the other. Okay? You think that works? Because the top is more special than the lower print? No, that doesn't work. And because this is not overloading in the sense that the top is more special than the below, because they don't have the different signatures. They have the same signature, just with an additional constraint to have a really overload where the one with constraint always wins if it fits. So this here, it's not clear which one is called. So you have to say here, no, and require here in the second one that this is not a view. That's the way you can do that. And that is the way this works. Okay, let's talk about a few other consequences of this view design. And one of the more interesting consequences is, let's look about what happens if we start to modify elements of the underlying range. So a couple of examples come now. This is a vector. We introduce a view that says, let's only take the even elements. Let's use that to iterate over the elements and modify those that are even, adding 2. And let's do that again. Works fine. Well, let's slightly modify this example. And instead of adding 2, let's add 1. Oh, works fine. What the hell is he talking about? So next time you do that, the first even element is again incremented, while the others are not. Yes, because we cache begin. Okay. Now, we knew about this problem when we standardized the filter view. So we came up with a perfect solution. That's sarcasm if you don't hear that. We say, you know what? This is undefined behavior. And this is undefined behavior. So in the C++ standard, we have an interesting command stated as a law. We say, for a key use case of the filter, which is fix broken elements, we have the following statement. Modifications of the elements of the filter view iterator is permitted, but results in undefined behavior if the resulting value does not satisfy the filter predicate. Done. So we are fine. We have solved the problem. Well, you have a problem now. You have to know this problem. But we did describe it. Only read the specification and you're fine. In general, we say this is an as on the wall paper rule. Which says we have a rule on the wall, and with that rule we are fine, although it's totally silly for you as a consequence. And it reminds me of a visit I had in 2011 in Brazil. And I just wanted to enter the elevator, the lift of a hotel. And I got the following sign. Okay, The hotel manager is safe now. We want you. So follow these rules and everything is fine. So you know what to do now when using the filter view. Which means, if we have something like this, let's find out, let's heal dead monsters in a computer game. So we iterate over the monsters that are dead, and we want to bring them back to life. That's undefined behavior. So you're not allowed to do that. Well, your program is broken. Do we have a MISRA standard for that already? No, it came too late. Because MISRA, the new one, is for C++17. Oh, you were so lucky. By the way, burning would be okay, provided burning does not bring back life to the monster. You never know. What is the solution? Well, one interesting solution is use a new filter the second time you iterate, which means use it ad hoc. This is undefined behavior, but it works. So that is the next thing we learned. Are we done with examples? I have a few others. So here's another. Vector piped into a filter. The vector is defined, then we insert a new element, and then we use the view. And we do that on the vector and on a list, and we print it out, and we see that this filter, because all the initial elements are not odd, but we later on added the 1, we get out, yeah, there's a 1. Works fine. Same for list. If you add a precondition for inserting a 1, if the view is empty, only insert 1, you have screwed up your program. In this case, we get the 42, because that is the place of the end, where formerly there was the end. This formally, I think, undefined behavior. I'm not actually very sure about that. But anyway, no, it's probably not. Because we have the offset. The offset was jump to the end. Now, the end is the 1, 2, 3, 4, 5, 6 element. Now, the 6th element is valid. So this code is probably valid. But broken. And if you do that with a list, because we don't cache offsets, we cache iterators, you really have undefined behavior. So anything can happen. Easy. You just have to know that. More examples? Okay. Taking a view on the list and filtering the elements. Let's insert a 0. And then let's print out the elements. So we have only the even elements, and that works fine. So when we print them out, 0, 2, 4 are the elements that are even. Let me insert 2 additional elements in the front, and let's print out the result. Interesting. So this, in a vector, this works. If you switch from a vector to a list, you have a problem. Why? Because O was the first element that was even, and now, accidentally, what we inserted as first element was also an even element. So that looks same. And then, but the list is broken, because we cached the position of the 0. It gets worse. Look at this example. Look at the middle and the output there. You are confused by this program. So what do? You insert a print statement. This print statement changes the behavior of the program. So once again, here in the middle, 024, 024. Now, 124 and 24, or 1. That's especially interesting because we break the filter predicate here. And also, look at the bottom, -1, 0, 2, 4, and 2, 4 is now coming here. Everything is screwed up. Everything is screwed up. Now, can we hear that? The usual question I have now is, well, can we uncache somehow? Well, you can copy the views. Well, if we copy a view, we have a problem if that is an iterator. But it's not a problem if it's an offset. So we uncache, in that case, only when we filter a list, but not a vector. So that heals the filter on the list, but not the filter on the vector. I would like to see some very interesting code here using that feature. In this slide, there's an interesting side effect. If you create the copy of a view, that has an impact. So a copy of a view does not have the same state as the original source. So let's come up with the final example. Let's have a print by value. So Peter, look. There we pass collections by value. And now let's have a set, filtering it, calling empty, insert one more element, and calling this function. Okay. We take the even elements. That should be 0, 1, 2, 3, 4. So it should be 0, 2, and 4. Great, works, fine. Hey, you should pass by reference. Okay, let's pass by reference. Not making the filter const, so we do it the right way. That's the output. So the behavior depends on whether we pass by value or by reference. And of course, on a few other things. And that is what we have designed in this standard. Oh my goodness. So, summary. One iteration where we read, one iteration where we modify but keep the predicate, one iteration where we break the predicate, multiple iterations going back and forth, and so on, and concurrent access. So this is a matrix, what is broken and what works. And by the way, some things are only broken because we cache. So without caching, we would have this slide. I think this is better. Well, but there must be a benefit of caching. So let me look at that. We have a range and a filter, and we have just some arbitrary elements. And let's iterate over these elements. So in the first iteration, we call begin. If it's pretty likely that the first element is in front, then we talk it, and then we iterate over all the other elements, looking at the value. So that's pretty expensive. The second iteration, yeah, we save a little bit. We call a couple of times end. That's the little arrows on the right there. And yeah, that's roughly, yeah. We have few benefits from caching in any iteration after the first one. So let's look at another use case. Let's have a long sequence of elements, and we have some fitting elements in the middle and at the end. So first element, begin, is cached. We iterate to the end. Second iteration, okay, we have benefits here. Good. Now let's not have valid elements at the end. Only in the middle, one or two elements. First iteration, well, we have to go to all the elements to look at the initial situation. We cache begin. Remember, we don't cache end. So next time we iterate, begin is cheaper, but if the distance between the last elements, fitting element, and the end is big, we still have to look at each and every value from there, even in further iterations. So we did not cache end. So we have benefits from caching in the second iteration for begin, but no benefit from caching with early last element. And this is always when we have 2 iterations or more. So are there use cases where we even have a benefit in the first iteration? Yes. The common example is you take a filter and then you reverse your iteration. So the reverse iteration comes from the other side, and then we also look at the begin, and then once we do it again, we call again and we are fast. The point is, in the original loop, we call begin once, but end multiple times, but this is reversed now. Now, reversing it means we call multiple times begin, and then we benefit from this caching. That's great. Unless you use the range-based for loop, because the range-based for loop calls begin and end only once, and doesn't call multiple times end. So here, we don't benefit from that, and have the same behavior as before. So in this use case, how can we make this use case fast? That's easy. Implement your own caching. Yeah, the filter caches, but it doesn't cache well. So what would I do? Well, in this case, I want to cache begin and end. So here's a way you can do that. You initially create a view that says drop all the elements that do not fulfill your predicate. Then reverse the iteration, and then drop all the elements that do not fulfill your predicate, and then reverse again, because otherwise we have the wrong order. That creates a view that has begin and end there. And that view can then be the beginning of where we apply these different filters, including reverse or not reverse, and they are super fast. That is super fast. That is the safe situation of the filter view. Do you like it? Do you like the design of the filter view? Okay. Let me summarize the situation. The current design of the filter view is not self-explanatory. We create unexpected errors, compile time errors, hard to understand why we have them. Create unexpected runtime errors, that's even worse. This makes the use of the filter view dangerous. We have undefined behavior in various standard use cases. And that means we require expert knowledge to use that, even for simple standard use cases, which means that some of the projects where we talked about that said, now we ban the use of views, of filter views from our projects. This is screwed up, to say it very clearly. And without a good reason. I don't know how compelling the motivations were here, the use cases where this pays off, compared with the other use cases, which are far more common. In my opinion, the filter view is seriously broken. So why did I vote it in? I was in the standard committee. It's my fault. I didn't know. We standardized with 200 people working on different areas. And to some extent, you have to trust. And if there are 10 people standardizing for 3 years, such an important and key library, I would definitely not have expected that we make that bad design decisions. We break a lot of rules of C++, screwing it up. I learned something. I don't trust anymore. What do you learn from that? How do you use the filter view? Well, beside the option, don't use them, you have the following options. Put filters early in the pipeline. Create and use filter views ad hoc. Do not modify elements with a filter. Or if you do not break the predicate. Or if you do, iterate only once, but the latter is formally undefined behavior, but it works. Do not use filters in concurrent code. No concurrent iteration and begin, or end, or from, or if. I didn't tell you all the problems. There's also a problem with const propagation, sometimes const, when the view is const, the elements are const, sometimes not, which is a break both with the ordinary containers and also an inconsistency in itself. So that is also a thing you should remember. And if you ask me what could you else do to get it better, well, maybe you submit a bug report to your compiler vendor or to the standard committee and saying there's a bug. The following code does not compile or does not work. Because that's the only currency the standard committee understands when they make mistakes. They don't want to fix standardized behavior because they have to explain what the fix does. We could fix that. We could just remove caching easily. And in some rare use cases, performance would be worse. Everything else would be fine. We didn't break binary compatibility, etc. We could fix that. Nobody of the group responsible for ranges sees a problem in the whole thing they have. They don't see any problem. They tell me just teach it, which I did. So now you know how to use the filter view. Thank you very much.